Good afternoon, everyone. My name is Mariia Golovianko. I am an associate professor at the University of Radio Electronics in Kharkiv, Ukraine, where I specialize in artificial intelligence, mainly in machine learning, in AI security, in various applications of artificial intelligence in Industry 4.0 and Industry 5.0. In today's presentation, I will be briefly discussing how we can improve current approaches to deep learning and how we can leverage expert knowledge and some domain expertise available to improve the performance and the efficiency of deep learning systems. I'll talk about the use of so-called informed machine learning for the tasks of optimization of network traffic and resource allocation, and as well as how we can use it to improve the transmission of the signals in networks. So I'm really excited to share some insights with you today and hope that by the end of the day you will understand a little bit more about our ideas and you'll understand what we are doing in this DIOR project. So recently, machine learning has shown tremendous success in models building across various applications and domains. And in our project in DIOR, we also see deep learning as an important enabler for signal processing and network traffic optimization in order to facilitate future high-capacity optical and radio communications. We see our work as a possible contribution to the intelligent networks beyond 5G. But sticking to traditional data-driven approaches of deep learning, we are risking running into a problem of building ill-performing and insufficiently generalized intelligent models. And the chances are quite big because we deal with increasing complexity of physical channel and network resources with their high-dimensional observation and decision spaces and the insufficient amount of useful data that we can actually use for training such complex systems as physical systems are. And complex systems typically have different components, multi-scale components. They may be influenced by various external factors. So it all makes this task of modeling complex system behavior very challenging. So another important aspect is that purely data-driven models might not meet constraints dictated by natural laws of physics, for example, natural laws of signal processing and transmission. Sometimes, very often, actually, these data-driven models are unexplainable and we cannot interpret the results of their work. So all this has led to the increased research in the field of machine learning. And the task is to find out how to improve conventional machine learning by additionally incorporating some expert knowledge available in the field, which was accumulated for ages. And the answer to this question is provided by the new field, which is called informed machine learning, which says that we can incorporate actually such type of knowledge. This new field or new paradigm of informed machine learning is actually facilitates a long existent aspiration of all AI researchers towards a fusion of bottom-up, data-driven, or so-called connectionist AI approach and top-down, symbolic or knowledge-driven approach to AI. So it's quite interesting to work with this informed machine learning, being a researcher in artificial intelligence today. So conventional machine learning starts with a specific problem, and there is some training data for this specific problem. These are fed to the pipeline of machine learning, which delivers some solution. This is a typical case. When we are talking about the informed machine learning, we are talking about learning from a hybrid source of information consisting of data and prior knowledge, so-called expert knowledge. The notion of knowledge here in this study is defined as some pre-existent validated information about relations between entities in certain contexts. And this prior knowledge should meet some requirements to be used in this type of informed ML. It should be pre-existent. It should come from an independent source, and independent from this machine learning pipeline and data set, and it should be formalized. And we have different forms of knowledge representations for this prior knowledge. This can be some logic rules, this can be some equations describing, for example, natural laws of physics, or it can be knowledge graphs, etc., etc. And this prior knowledge should be integrated into the machine learning pipeline in order to provide some solution. There are different ways how we can integrate this prior knowledge into the machine learning pipeline. And the survey helped by the researchers from Fraunhofer Institute for Intelligent Systems and Information System, for Intelligent Analysis and Information Systems, I guess, yeah, introduces a classification framework or a taxonomy, splitting all the approaches existent in this informed machine learning area into categories according to three big aspects. The first aspect is the source of the information or source of this prior knowledge. The second aspect is knowledge representation that is used. And the third one is how this knowledge is integrated into the machine learning pipeline. And they showed that there are three big sources of information, of this expert knowledge. They could be, this prior knowledge could come from as rather specialized and formalized scientific knowledge. It can come from our real life, from our everyday life as a world knowledge, or it can be some more intuitive expert knowledge, which some experts provide for us. So they also say that there are, according to existent research in this area, 8 types of knowledge representation which we can use for integration of such prior knowledge into machine learning. They are here on the slide. Among them are algebraic equations, differential equations, simulation results, etc., etc. And according to the research regarding integration of this prior knowledge, it is possible to integrate this prior knowledge at every stage of machine learning process. So it can be integrated either to training data or hypothesis set over learning algorithm or to final hypothesis. Deep physics-informed neural networks or physics-informed machine learning is one of the most interesting and successful emergent approaches of informed machine learning. So it's one option how we can use this informed machine learning. Actually, despite relentless progress in physics studies, and it's become obvious that traditional analytical and computational approaches cannot deal good enough with modeling complex systems and complex processes, complex physical processes. This is why observation data and machine learning on top of it plays a huge role in further studies and further progress in this area. However, despite the availability of various public data sets and data, there is not so many useful data in this area. There is a limit of the useful experimental data is very limited, actually. So insufficient separately expert knowledge and observational data integrated into one framework become a very powerful instrument and a very powerful source of information on how to identify multidimensional relations, correlations, and manage ill-posed problems. In physics-informed neural networks, this analytical knowledge, for example, refers to governing physical rules described by with help of differential equations, for example, which is a kind of algebraic equations. And so, in fact, pins, while learning, they perform multitask learning, simultaneously fitting the observational data and reducing a partial differential equation residual. In particular, pins or physics-informed neural networks can be used to model and simulate a wide range of physical phenomena, including fluid dynamics, mechanics, structural mechanics, quantum mechanics, climate science, etc., etc. And in our work, we would like to check how physics-informed neural networks and other informed machine learning approaches can be used for signal processing and network traffic optimization, for future high-capacity optical and radio communications. And as researchers in artificial intelligence, we are mainly planning to develop new approaches to informed machine learning, and probably develop some new tools that can be used in many domains and areas. Among them is optical and radio communications. So that is our plan for the DIOR project. Thank you for your attention. I guess that's all for now.
That's wonderful. Thank you very much, Mariia, and also for keeping the time perfectly according to the schedule. That's a very good timing, and I appreciate the detail and very insightful talk about this interesting topic. One question, we probably have time for one, but as usual, if anyone wants to add, please do join. So just to delineate a little bit better this novel approach from already existing ones, could you just elaborate a little bit, please, on the incorporation of prior expert knowledge? It seems like we can say that in many cases it's already incorporated in the traditional machine learning approaches. Could you just talk about what specifically differentiate this novel approach?
Yeah, actually, incorporation of expert knowledge is not news for for machine learning, for traditional, conventional, so to say, machine learning. But actually, usually when we are talking about the incorporation of prior knowledge in traditional machine learning, we are talking about some data preparation, such as labeling of data set or feature engineering. Moreover, we usually see this incorporation of prior knowledge as some dependent process, which is very intertwined with the machine learning pipeline. So this prior knowledge is not coming from some external source of information. It is not independent. And so it's absolutely different from what we have in this informed machine learning. So the main point is that here we deal with some absolutely different source of information with a different knowledge representation type and with some pre-existent knowledge, which wasn't used previously.